Hello, everyone. This is Jianhua Mo from Samsung. We are excited to share about our latest research output from Samsung Research America Standard and Mobility Innovation Lab, which is located in the Texas, USA. This is also a collaboration work with Samsung headquarters in South Korea. And the research is about subchain beam for mmWave device. This is a new scheme proposed by us to achieve a good trade-off between the power saving and the beam correspondence. First, about the motivation. As we already know, the mmWave array, antenna array are adopted to support the mmWave 5G UE to increase the beamforming gain as well, and then you can achieve higher throughput. So in the figure on the right, there are two antenna arrays located on the left edge and the right edge of the phone. And each array has 1x5 antenna elements. So the bad things about this larger antenna array is the more power consumption. So the power will increase linear with the number of active antenna elements. So as the power consumption goes up, the temperature also goes up. And this is not tolerable for the UEs. So in the phone operation, the system will continuously check the temperature. If the temperature is too high, for example, about 40 degrees, it will go fall back to the LTE mode. So this will reduce your peak throughput since you go to the large bandwidth mmWave band to the relatively narrow bandwidth in the middle or low band. The second disadvantage is that this frequent turn on and turn off of the mmWave antenna, it will incurs additional latency and power consumption. So based on the latest report from OpenSignal, the average time that the 5G phone connect to a mmWave 5G network in the US is just less than 1%. So this is a quite low penetration rate for mmWave 5G. And this power consumption is one of the issues. And in this work, we propose to use subchain beams. This can help reduce the chance of the LTE fallback and increase the penetration rate of the mmWave 5G. So this shows some simple examples of these subchain beams. In these tables, there are K beams for each beam codebook, and each column represents one beam codebook. And from the first column, which is a full chain beam, you have to activate all the 5 antenna elements. For the full antenna beam case, you only activate 4 out of 5. So here, the 0 means the antenna element is not activated. In this case, there are only 2 bit shifters, so the possible phase shifters is just the 1J minus 1 and minus J. If you have the subchain beam codebook and when you do this mmWave 5G operations, you can you don't have to go back to LTE directly when you have these overheating issues. You can go from the subchain beam to reduce your transmit power, or and then you can control the temperature. For example, you are currently at five antenna elements working. Now, if you have the power issues or temperature issues, you can deactivate 1 out of 5, and you can reduce 20% of the power. But there are several challenges about these designs. One challenge is the downlink-uplink beam correspondence. This is something term defined by 3GPP standards, which means that the best RX beam in the downlink direction should also be the best TX beam in uplink directions. The reason is that currently, the 5G standards, they only define the downlink beam management. There's no uplink beam management procedures right now. So the UE choice for uplink beam heavily rely on the downlink beam sweeping. So this beam correspondence means that if the 5-chain beam 2, which is shown in the left figure, should also be the best TX beam in the right figures in the uplink directions. So note that the left figure shows the full chain beam, and the right figure shows the subchain beams. So here we assume they have the one-to-one beam correspondency from B0 to another B0. The left B0 corresponds to right B0s, and so on and so forth. The second challenge of this beam design is the spherical coverage requirement, which means that you don't have a clear or obvious coverage hole in these angular domains. So for example, the right figure shows one design where you can see clear there are some hole between the B2 and the B3. So in summary, you have the two design constraints. The first constraint, which is beam correspondence, it care about horizontally the beam relationships. You want each row you have the beam similarly, so you still have the beam correspondence when you change the number of antennas. And in the vertical direction, you also have the spherical coverage requirement. That means for each given number of antennas, your codebook should have a good spherical coverage. You don't have clear coverage hole in any directions. So according to this challenge, we propose 3 different design metrics. The first one, similarity score, which is only care about horizontal directions. It try to ensure the interchain beam correspondence, so you can avoid the beam sweeping when you change the number of antennas. The second design metric is the spherical coverage, which is basically the opposite way. You care about vertically the spherical coverage. And the last one, the design metrics, BCSC, which is a beam correspondence spherical coverage. So this is a metric which between the similarity and the spherical coverage. We will use some simple examples to explain these 3 different design metrics. This is the first similarity metric. In the figure on the right, we see there are 3 full chain X beams, A1, A2, and A3. And for the subchain beams B1, B2, B3, we designed the B2 to mimic A1, design B2 to mimic A2, design B3 to mimic A3. So in this sense, when you change the number of antennas from the full chain to subchain operations, you don't have to sweep this B1, B2, B3 to identify the best beam. You just pick one. So for example, if A2 is best receive beam, you then choose B2 as the best transmit beams. So this one is good for the case you have this low latency requirement, for example, the URLIC application scenarios. So we have some concrete idea to solve these problems. This problem is just to calculate the correlation between the full chain beam GI and the subchain beam BJ and try to maximize the similarity score. And this method is reuse of some of the data-driven method we propose in this R1. We'll omit the details here. And the second metric is called the spherical coverage metric, which care about vertically the spherical coverage of each beam codebook. So in this example shown on the right, the B2, B3, B1, B2, this is another subchain beam codebook. It tries to maximize the spherical coverage. So that means there is no clear coverage holes in these angular domains. However, there is no clear one-to-one mapping between the full chain beam and subchain beams. That means you need a beam sweeping when you change the number of antennas. So the advantage of this symmetry is that you can achieve good spherical coverage for these subchain beams. So this can apply to the area the scenarios where you care much about beamforming gain. For example, you have this UE with low gain antennas, or you have a small antenna arrays. So you want to use this asymmetric to design subchain beam codebook. And we have used the Kmeans algorithm to design this one. So this is some reuse our previous work about Kmeans algorithms, which is an iterative algorithm to design the beambook to avoid any coverage holes in this angular domain. And this algorithm usually converges very fast within a few iterations. And last one, the BCIC metric, which is something between the first and the second one. So in these simple examples, we first identify the convergence of this A1, A2, A3 matrix. So we notice that the boundary is 20 degrees between A1 and A2, and the boundary between A2 and A3 is located at minus 30 degrees. So given these three angular regions, we designed the B1 to maximize the beamforming gain in the region where the angular angle is larger than 20 degrees, and so on and so forth for B2 and B3s. So for this one, this is something they achieve the two objects together. So you still have the similarity, similar or resemble the full chain beam. As well, you can also achieve the good surface coverage. So the details will omit here. We will show you the simulation result. This is the case. You have the 14 beam codebook, and you have these two linear array of 5 antennas, and the 5-bit features are adopted. We show the BCIC maximization as the design metrics. We also have the other design metrics result in the appendix if you want to check. So here, starting from the first one is the 5-chain or the full chain, and then the second one is the 4-antenna subchain codebook, and the 3-antenna, 2-antenna, and the 1-antenna subchain codebook. So as expected, the beamforming gain will reduce from the 5 antenna to 1 antenna since you have 1 antenna deactivate. However, if you look at best beam index distributions from 5 to 1 antenna subchain codebooks, you can see the best beam directions or best beam index distribution, they are almost the same. They don't change too much when you go from 5 to, for example, 3. So that means in your similarity is still preserved by using the BCIC maximizations, and your interchain beam correspondence is preserved. When you go to 2-chain and 1-chains, as expected, you have more and more difference compared to the 5-chains because they have a big difference. However, they are still not so different. So in roughly, they are still have similar color distributions in the angular domain. So also we evaluate the 3 different designs in different metrics. So first, if you consider similarity score, then of course the codebook design with similarity is the best one, which is the black curve. And the case with the BCIC, the red curve is the second best one. It's better than the yellow one, BRC maximization beam codebook. And about the spherical coverage comparisons, we can see that the dash curve, which is RC maximization, is the best one. The dotted dash curve is the best one. And the dash curve, which is the BCIC, is very close to the dotted dash curve. So that means the BCIC is also good in the spherical coverage. So in general, in conclusion, we see this power saving and the temperature control is a big challenge for 5G mmWave penetration rate. We propose to use this subchain beam codebook to avoid the LTE fallbacks by controlling the temperature. And we present different metrics or different methods to design subchain beam codebooks. The purple design of BCIC maximizations, that's we thought as a good choice because it optimizes both the interchain beam correspondence as well as the spherical coverage. Thanks for everyone. If you have any questions, please send the email to me. Thanks, that's all.